Hello and good morning. Now this topic is based on work and heat transfer. It's part of thermodynamics. So basic content is taken from P.K.NOC book, Basic and Applied Thermodynamics, Tata McGraw-Hill books. Okay. First we'll start with thermodynamic laws. Thermodynamic laws, there are different laws. First law, second law, third law, and zeroth law. Okay, there are 4 laws. Okay. So zeroth law says, like, if A is in equilibrium with B and B is equilibrium with C, so A and C must be in equilibrium. First law says that energy and work can be convertible. Second law says 100% work or energy cannot be converted, because whenever heat is converted into work, so some energy will be lost. Third law says, like, it is for absolute a perfect crystal will have at zero entropy at 0 Kelvin. So ideal gas. So in ideal gas, formula is that PV equals nRT, universal gas constant, N number of mole, T is temperature. Okay, and for 2 states, P1 V1 by T1 equals P2 V2 by T2. Okay, these are coming from your basic equation, Boyle's law, Charles law. So Boyle's law says PV equals constant, and there is criteria. This Boyle's law will be holding true if the process is very slow and isothermal. Okay, and for low pressure application. So when Boyle developed this formula, so that time there was no machine to create a very high pressure. So because high pressure was not created, so this can be applicable for low pressure application, and it must be very slow process, not very fast process. Okay, and Charles law says PV equals nRT. Okay, so when pressure, volume, and temperature linked, that is coming from Charles law. Okay, now temperature scales. So temperature scale, I already told, centigrade is there, Fahrenheit is there, and Kelvin. Basically these 3 scales are common, and there will be a Rankine also. Okay, so I'm not going to Rankine now. So centigrade, like freezing temperature 0 degree, Fahrenheit freezing temperature 32 degree, and Kelvin will be 273 Kelvin, and freezing. Okay, and if I go to boiling point of water, freezing point, actually water at atmospheric pressure. Okay, if pressure is changing, the freezing temperature, boiling temperature will change. So whenever you are talking about freezing temperature or boiling temperature of water, you have to specify pressure also. Okay, so boiling water, this is 100 degree, this is 212 degree, 212 degree, and this is 373 degree. Okay, so C to K conversion is very easy, just add 273. Okay, C plus 273 is your Kelvin, but C to Fahrenheit formula is that C by 5 equals F minus 32 by 9. So this is the conversion formula. So if you know certain temperature in Fahrenheit and you want to convert into Kelvin, so it is simply you convert to Celsius, then add 273. So that will be easiest process. If I can write directly, F minus 32 by 9 equals K minus 273 by 5. So this also can be possible. Okay, a closed system and surrounding can interact in 2 ways, by work transfer or by heat transfer. This may be called as energy interaction. Energy interaction. In closed system, in previous lecture we have seen this closed system means mass cannot enter or exit, rather energy can enter and exit. Okay, so two way it can interact, work transfer or heat transfer. Okay. Now surrounding, if I have surrounding, this is system, work will be going surrounding, ending surrounding. So what is work is going out, so W is positive. Okay, but system work incoming, so in that case surrounding, so W will be negative. Okay, the work PdV work and displacement. So first you draw the figure P V, and let's say one process is happening like this, 1 to 2. Okay, take very small amount of volume change. So this is volume V1, this is volume V2, and this is dV. Okay, and this process happening like this. I have one piston cylinder arrangement, and P will be acting in all direction because of Pascal's law, P1, and V1 is here, P2 is here, and piston is here. Okay, V2 is here. Okay, this is process 1, piston is here, piston 1 position, this is 2 position. Okay, now if I draw this one on piston, it will be like this. Okay, and piston initially here. Okay, piston is here, and P is working here, P. Then this is dV, actually this area is dV, and piston is here. Okay, when piston moves infinitesimal amount dl, so it is dl moved, dl, AP is the area, so this piston area is AP, so volume will be AdP, so volume will be AdP, because A is not changing, area, piston area is not changing, only the motion is changing, so the volume will be AdP, sorry, AdL. Infinite. Okay, now infinite work dW equals F into dL equals P into AP piston and dl. Okay, piston area I say AP, A suffix P. Okay, so W1 to 2 work is V1 to V2 P dV. Okay, this is work done. So PdV work in various quasi-static process. Okay, so a constant P equals constant, isobaric is called isobaric or isopiastic, isopiastic process. Okay, so it is like this. P process is here, constant pressure, P is not changing, 1 to 2, so this area V1 V2 V. Okay, so W12 1 to 2 is V1 V2 P dV, P dV equals P into V1 minus V2 minus V1. Okay, because pressure is not changing, so it becomes V2 minus V1. Another condition is that constant volume or isobaric, isochoric. Isochoric process. So there is like this, P V process is like this, 1 to 2. Okay, so this is P and W12 integration of P V1 V2 P dV. So volume is not changing, so it is becoming 0. Okay, and C process with PV equals constant. So this is Boyle's law when it is system is isothermal. So it is like W1 to 2. So process will be like this, 1 to 2 P V. This is V, this is P, this is V1 V2. Okay, integration of P dV, V1 V2 equals P we know P V equals P2 V2 equals constant. Okay, so this implies P equals P1 V1 by V, or I can write PV only. P equals okay. Now W12 1 to 2 equals P1 V1 integration of V1 V2 dV by V equals P1 V1 natural log dV by V. No, natural log V2 by V1. Okay, because this is coming logarithm, and if I replace P and V, V by P, then it will be like P1 V1 natural log P1 by P2. If PV equals PV power n equals C, this is a diabatic process or polytropic process. Let's say assume polytropic. So PV power n equals P1 V1 power n equals P2 V2 power n equals constant. So P equals P1 V1 power n by V power n. So W1 to 2 integration of V1 V2 P dV equals V1 V2 P1 V1 power n V power n equals dV. Okay, now we replace P by P1 V1, so it is becoming like this, P1 V1 power n V minus n plus 1 minus n plus 1 V2 by V1, P1 V1 power n 1 minus n V2 1 minus n minus V1 1 minus n. So it is becoming P1 V1 minus P2 V2 n minus 1. So it is P1 V1 n minus 1 1 minus P2 by P1 n minus 1 by n. Okay, so figure will be like this, P V, okay, and 1 2, okay, so just different line I'm showing. This is V1, this is V2, n equals 1, n equals 2, n equals 3. Okay, so this is process. Not here. this is process PVN equals constant, and here okay, so if n equals 1, it's becoming PV equals C, so that becomes Boyle's law. So PV energy work when you are calculating, so we need to go through integrated diagram. Integrated diagram, first you draw one slider crank mechanism. I have one cylinder. Okay, cylinder is like this, two valves are there, and there will be one port here. Port will have another piston. Okay, piston is here, and piston is connected to one stylus, and this cylinder is having one piston. Okay, piston is connected to one slider crank mechanism. Slider crank mechanism like this. Okay, so this is crank. Later stage when we will discuss IC engine, there will explain much more details. So just here if you rotate crank, this piston like thing, it will be moving forward backward. Okay, so this is called cross head, and this is connecting rod. Okay, then piston, this is also one piston. This is similar to an IC engine actually, and piston, this cross head will be connected to one stylus. Okay, cross head is connected with R. Now this, I'm putting some dots, this there will get indicator diagram. If piston is moving forward backward, okay, because of crank rotating, that's why crosshead will be moving forward backward, and crosshead is moving forward backward. This will be pushing piston also move forward backward. When piston is moving forward backward, that inside this area it will be compressed or expanded. When you are compressing, let's say both right side valves, okay, right side valves are closed, then when you're compressing, pressure will be increasing. So pressure will be increasing, temperature will be increasing. So that will be indicated in your indicator diagram. Okay, so I have written this diagram, indicator. Okay, so the top section indicator diagram is there. So there we can get a diagram actually. Okay, when pressure is increasing, the volume will be compressed. When volume is compressed, so you will get certain curve. When you are expanding, you will get a certain curve. Okay, so PV, if I draw PV, normally indicator diagram will be coming like this, going like this, it will be going to expanding. Okay, and if there is no heat transfer is happening or no work transfer happening, so 1 2 1 it will be happening like this. But if work transfer, heat transfer happening, then curve will be a little bit different. This is called indicator diagram. Okay, and this inside area of indicator diagram is the work done. Okay, work done in one engine cycle, okay, this thing I'll discuss later also in details when I'll be discussing about IC engines. Okay, the area of the indicator diagram represents the magnitude of net work done by system in one engine cycle. So this area will be showing that how much work done by the system. Okay, now if I have 2-stroke engine, 4-stroke engine, IC engine, so I'm not going into details this IC engine now. Just here you can see this indicator diagram we can draw, and the curve in between that area is called how much work, the intensity of work we are producing. So for 2-stroke engine, work done, later we'll discuss later. 2-stroke work done per minute. So P M A L N. What is A? A means area of piston. Area of piston. N, number of stroke. And L is stroke length. So total volume into P is the average pressure. Average pressure in the cylinder, and total volume, how much composition decomposing. That if you know, then you can get per minute work done, and number of stroke per minute. Actually N is number of stroke per minute. Number of strokes. Okay, that way you can calculate 2-stroke engine work done per minute. But if you have 4-stroke engine, then it will be divided by 2. For 4-stroke engine, it will be like work done PMALN divided by 2. What happens in 2-stroke engine, in IC engine or internal combustion engine, motorcycle, bus, truck, your crank is rotating. So when it is rotating, one time it is giving power, one rotation, one time power. But in 4-stroke engine, what is happening? The crank will be rotating 2 times and you will get 1 time power. That's why divided by 2 is coming. Later we will discuss details when we will be discussing IC engine. Okay. Power developed inside the cylinder of the engine is called indicated power, or IP. Okay. Power developed inside the cylinder is called indicated power. Indicated power IP. So the formula is that PMALN or N by 2, because of 2-stroke or 4-stroke engine, divided by 60 in kilowatt. Okay, power in kilowatt. Okay, unit. So PM in kPa, PM kPa, and N, number of cylinder. N okay, N also you can put. So N, number of cylinder. Okay, here I am using N, but I have used another N in PV power N. So both are different actually, don't mix up. Okay, N is number of cylinder. If I have 1 cylinder, then N is 1. If I have multiple cylinder, then number of cylinder will be 2. Many marine engines will have multiple cylinders. Okay, normally there will be no single cylinder for very heavy ships. Cargo ships or passenger ships or big cruise ships, they will have multiple cylinders. Okay, but small engine, for example motorcycle, bike, scooter, and the small fishing boats, they may have only 1 engine, 1 cylinder. Brake power, another term is brake power. Brake power is equals BP, or torque into omega. Okay, torque means shaft torque, how much torque is there and how much rotation is there. Rotation means revolution in radian. Okay, and T is torque, and omega equals 2n pi by 60. N, here N is shaft rotation. N equals shaft RPM. Okay, so here I am using N for other purpose also, so please don't mix up. Okay, N means NR, I can put some suffix so that it will be different. Okay, mechanical efficiency. Mechanical efficiency, eta mech equals BP by IP. Okay, indicated power means inside engine how much power we are getting, so that is higher. And brake power means after engine lots of friction will be there, then you are getting power. Okay, engine is giving higher power, then there will be certain losses, because second law already we discussed. The second law means there will be certain losses every time. Okay, indicated power is higher, then you are getting shaft power. Shaft power means brake power, so that brake power is lower than your indicated power. So what is the mechanical efficiency? Whatever you are getting divided by your engine power. Okay, that is called your mechanical efficiency. So BP by IP. Heat transfer. Heat is a form of energy. Okay, this is also energy. So let's see PV diagram. P and V. V means volume, pressure P, and T means temperature, X means distance. Okay, so 1 to 2 one process happening, another process happening 1 to 2, but it's represented on TX coordinate system. So area, this is area. Okay, this area is equals work transfer actually. Transfer, okay, equals W1 to 2 P dV. So area area equals heat transfer. Okay, so this is heat transfer area. So Q1 to 2 equals 1 to 2 T dx. Okay, so representation of work transfer and heat transfer in quasi-static process on PV diagram, TS diagram, it is there. Okay, so here system and work is giving to the system, that is negative. Okay, we have to use negative sign. When work is going out of the system, we'll be using this is negative, we'll be using positive sign. Okay, and heat transfer case, system, this is also system. Okay, Q entering, this is positive, Q exiting, negative. Okay, so specific heat means C equals Q by M delta T. Okay, so unit will be joule per kg K. MC called heat capacity. Okay, later we'll discuss in details of these terms, and we'll do some calculation also in the heat transfer lectures. Laws of thermodynamics. So first law. So first law is, it is an energy conservation law. First law is the energy conservation law. Energy conservation. Okay. Second law says energy loss, which is concept of entropy. It will give concept of entropy. And third law, a perfect crystal should have 0 Kelvin temperature. So 0 Kelvin concept it will give. And zeroth law, it will be talking about equilibrium. Equilibrium. Okay, in first law, energy can be converted to work, work can be converted to energy, and they does not say but how it will be done and whether there will be energy loss or anything. But in second law says that energy 100% cannot be converted. Actually, there will be certain losses every time. So this second law is very much important for our all calculation marine engineering, because whenever there will be one boiler transferring heat or transferring steam to turbine is giving power, that power is being transferred through shaft to propeller. So every time there will be energy losses. Okay, we cannot generate any system which will be self-sustaining, so we cannot design any perpetual motion machine. So any machine will be running by itself without taking outside any energy. Okay, this second law confirms that, but first law does not say that. Okay, first law says energy can be converted, but how it will be converted, how much converted, that does not say anything. Okay, so first law formulation, if I write, it will be like summation of W cycle equals some conversion factor summation of Q cycle. Okay, so Q minus W equals delta E. Internal energy, increase in internal energy. This is increase in internal energy, and this is net energy transfer. Okay, so regarding second law, the entropy we'll discuss later. Enthalpy. So enthalpy is the intrinsic property. Okay, and the formula is like H equals U plus PV. U means internal energy, so this is called specific enthalpy. Okay, and PV is pressure and volume, and unit will be kJ per kg. Okay, for ideal gas, H equals U plus RT. Okay, perpetual motion machine, first kind. There are two types of perpetual motion machine. This is first kind, is coming from first law, and another is there PMM2, perpetual motion machine of the second kind. They're coming from second law of thermodynamics. So first law says that energy cannot be destroyed or created. Okay, so and there will be certain losses actually, and from same source you cannot take and give back energy. Okay, so when you cannot take and give back, so that means you cannot get work also. Okay, so first law says that helium gas, actually helium gas from a bottle, inflated elastic balloon, it is inflating. The balloon was originally folded completely flat to vacuum of to a volume of 0.05 meter cube. If the barometric pressure is 760 millimeter Hg and mercury, what is the amount of work done upon the atmosphere by the balloon? This gives the system before and after the process. Okay, so first you draw the bottle. Okay, bottle means we are assuming glass bottle, so there will be no change in volume or shape or the boundary of system boundary. Okay, and initially it was flat like this, so this is balloon initial flat. Okay, and after blowing it, it will be P2. Okay, and final volume 0.5 meter cube. Okay, this is helium gas is here, and atmospheric pressure, P atmospheric pressure 760 millimeter Hg. So it is becoming like almost 101.325 kPa. So initial PA initial pressure P1, final pressure P2. Okay, now work done, WD equals integration of PdV plus PdV, and first PdV is a balloon, second is a bottle, and second PV volume is not changing, so that is equal to 0. Okay, so it is becoming like PdV balloon plus 0. Okay, so 101.325 into 0.5 is becoming 50.66 kJ. Okay, so plus sign becomes because work is done by the system, because work is done by the system. Okay, and minus 50.66 kJ if you write, then it will be work done by the atmosphere, work done by the atmosphere. Right? So another problem, the piston of an oil engine of area 0.5 square meter moves piston surface area. Okay, moves downward 75-meter, drawing 0.00028 meter cube of fresh air from the atmosphere. The pressure of cylinder is uniform during the process at 80 kilopascal, while atmospheric pressure is 101.325 kilopascal. The difference between the being due to the flow resistance in the induction pipe and the inlet valve. Estimate the displacement work done by the air finally in the cylinder. So first draw this cylinder. Okay, so initially it was here, so volume was 0 and final volume become like 3.375 into 10 power minus 4 meter cube. Okay, so piston stroke equals 0.0045 into 0.0 into 0.075, it is becoming 0.00033375 meter cube. Okay, now del V we got no, not this is not piston, this is volume of piston stroke. So actually this is delta V. Okay, now as P is constant, it's 80 kPa given this data. So work done equals PdV. So equals 80 pressure into dV, 0.0003375 kJ. So it is becoming 0.027 kJ equals 27 joule. Okay, so this is the energy we get.